Thank you, Steve. Welcome everybody to today's CAV meeting. I think as Danning, do you have the slides?
Yeah, I think it's being shared, right? Is it?
While Danning's doing that, I'm Carl Reichert. I'm with the graduate program in acoustics and with the Applied Research Lab. I'm also associated with the affinity group for systems and structures health monitoring. If you attended the annual CAV conference last fall, you'll remember that we had a workshop or I forget what we called it, maybe a panel session on AI and machine learning in acoustics and vibration. And there was a lot of interest in that. We had good attendance at the workshop. We had several people who were very interested in contributing. We actually had more contributors than we had time for, and decided that we would try it out to see if there was enough interest in a separate working group in AI and machine learning. We're introducing that at today's meeting here. Danning is pulling up a couple of slides that talk about the AI and machine learning roundtable that we had. And we'd ask that you email each of us. You can copy both of us or just email one of us if you're interested in being on the mailing list for the AI and machine learning group. And that will make sure that you get invites for future meetings for this group. And we will probably be reaching out to interested parties to help us focus the scope and of what we're going to kind of consider within the realm of AI and machine learning, and also within kind of the scope of the CAV. So as you see on the slide, we had several panelists from industry and universities last fall. Go ahead, Danny.
Yeah, I can go from here if you want. Yeah. So we had this panelists and we presented a lot of recent machine learning work on acoustic and vibration. Here are some are from our colleagues, like the lower right is from Eric, and I'll get one from Dr. Dare. And also I think the one is from Dr. Reichert here. Anyways, we had almost unanimous consensus that we need to start a machine learning group, and we need to address some key challenges that's now in this field. That's we want to incorporate physics and all these fancy data models to get a robust and explainable machine learning model that can be used robustly in industry. And this also connects to the questions that arise from this roundtable. Questioning are all these fancy data models are applicable to solve real questions, real problems in the industry. And then parallel to that, we also have discussions on what should we train or develop the students or prepare them for the industrial work, where we do need them to have the get both the math and the hands-on skills and so on. And this ends up with our essential needs that we identified. As Carl said just now, we want to bring people from the different applications in acoustics and vibration, and then get people working together to solve some problems that are probably challenging in real industrial scenarios, and let's solve them together. And to do that, we apparently will leverage just a broad spectrum of machine learning methods, starting from the more conventional supervised learning and to more recent, like network theoretic or operator theoretic methods, and also to a lot of more advanced concepts like active or reinforcement learning and things like those. But in the end, we want to be able to solve the traditionally challenging problems in acoustics and vibration in the realistic industrial scenarios. And then based on these motivations, we have listed our current research topics of interest, which ranges from reduced order modeling of very complex multidisciplinary systems to like information fusion and decision making based on, for example, the health monitoring systems. Of course, as our group grows, I'm sure that our topics will continue to evolve and expand. And then, and so far, Carl, do you want to talk about the recording, about the emails, just to emphasize again?
Sure, thank you, Danny. Yeah. So that's a quick overview of what we hope to, kind of a little bit of background of what we hope to accomplish with the new working group. So we're putting out a call to recruit members from the CAV and from across campus. If you're involved in the CAV already and you're interested in participating in this working group, please let us know. And if you are not currently a member of the CAV and you'd be interested in following the work that we're doing here and participating, please send us an email. Both Danning and my emails were there at the very beginning, or you can just look us up on the Penn State directory. And then we will put together a mailing list, an email list, and we'll probably get back to you with other information that we typically like to track for the CAV, things like what kind of projects that you're working on that fall into this area, what graduate students you have that are contributing to those projects, and any industry partners that you can think of that, or other people that you think we should reach out to that maybe we missed with this invitation. And we'll get the group going. Like I said, we'll refine our focus, kind of decide what we want our scope to be, and hopefully we'll have a good representation of the AI and ML community here at Penn State and within the CAV at our next annual conference.
Hey, Carl, this is Steve. Just to point out, this is an AI machine learning group for vibration and acoustics and related activities. So it's not a group for all AI and machine learning stuff. So it is focused on typical CAV activity. Right.
That's right, Steve. Thank you. Yeah, we're trying to focus this effort on applications in vibration and acoustics to kind of fit within the charter or the scope of the Center for Acoustics and Vibration.
Yeah, and in parallel to these member recruiting and technical interactions, we are also planning some other activities, maybe some kind of summer short courses or some training for the students in the related fields in acoustics and vibration to equip them with correct tools to apply or practice the machine learning tools. Yeah, and then yeah, I guess that covers all our informations concerning this new group. And here comes to a quick discussion session. Like if the audience want to ask about what's your interest in machine learning, or what do you want out of this group?
Okay. Well, thank you, and you feel free to put any thoughts you have on the group in your emails to Danning and myself, expressing interest in the group. So I think with that, we'll turn it over to Danning for his presentation for today.
Okay, yeah, thanks. And I will turn on my, wait, why it's still playing? Okay. Yeah, let me pull out that slide. Does the slide show up? Maybe it's not.
Not yet, Danny.
Okay. Let me maybe reshare the screen.
There you go.
Okay, does it show up now?
Yep, now we have it.
Okay, great. All right. So now the technical part. Yeah. So here I will be mainly talking about part of my work on hypersonic vehicles, or specifically the aerothermoelastic analysis of hypersonic structures. And in this process, I have used quite a bit of machine learning to enable this design process. So starting with hypersonic, it's basically just meaning that we are flying really fast. And a joke that I used to make for hypersonic is that with that capability, we should be able to go to Asia to get some authentic Asian food instead of American Asian food, and then still work in America. And this can be just done in one day, which seems to be charming. However, there are some technical barriers, and one of this is what we call the aerothermal elasticity. And actually, this semester I've been teaching aeroelasticity. And if you are familiar with aeroelasticity, you would be probably you'll know for sure this called what we call color triangle. It is the triangle of the aerodynamics, inertia, and the elastic forces. They form a triangle that's fundamental of the aeroelastic behavior. However, if we think about hypersonic vehicles, then we first need to account for the thermal effects, which are due to the really high speed flow that impacts on the vehicle, that heats up the vehicle structure. And all of these deformation will cause the deformation of the vehicles, which then will impact our control surfaces and our propulsion system. And therefore, it can end up with an octahedron for hypersonic vehicles. And in the middle is our term aerothermal elasticity. Yeah, and here's just one example of what might happen for aerothermal elastic behaviors. Here is the Lockheed Martin kind of design of the vehicles. If we look at the surface, just the skin panel, for example, down in the lower surface, the panel might heat up and it might buckle and might enter some unstable behavior called a flutter. And if this happens, it will be really, really dangerous because the structure might just break and the entire aircraft will crash. So there comes to our need for stronger and lighter structures. And here's a figure showing the thermal design considerations of the structure. For example, just now we are looking at the external skins. So as we increase the cruise Mach number, we'll see that this structure will operate in the range of 1,000 to 1,500 K. I know the unit is K, so it's slightly more severe than Fahrenheit. And you can imagine what would happen for a structure when it's like 1,000 K. It will be thermally expanded, and sometimes more severe behaviors on the material might happen. And furthermore, if we look at the inlet for the engine, it's even more crazy. We are having temperatures that might reach 2,500 K. This is even maybe beyond the limit of some materials, the best materials that we have for the thermal environment. And then what's the result for these thermal effects? Probably many of you know this X-15, this classical configuration that NASA has been playing with. It has been tested over a wide range of Mach numbers, and what people have seen is that there are so many destructions or malfunctions due to the thermal effect. Like on the in the middle here, we are having a protrusion for the antenna, and due to the aerodynamic heating, it's almost damaged after the flight. And really, we need very strong structures, but still it has to be light enough such that we can have the vehicle actually flying in the air. So this is our basic challenge in the aerothermal elastic design of hypersonic structures. So then what are the challenging part for the aerothermal elasticity? Well, first of all, we of course will have three components: the fluid, the thermal, and the structure part. And the thermal part, the fluid part is apparently very challenging, as you might imagine. And here is one example where is some recent work that I'm doing with the Santiago National Lab, where we try to analyze a control surface that's exposed to hypersonic flow. And you can see there are many complex flow phenomena, like we have a shockwave boundary layer interaction at a high speed. We have a boundary layer transition that's a totally different animal from the case of subsonic or supersonic flow. And besides these, we also have things like a real gas effect, where because as the gas heats up, the molecules might dissociate and be chemically reacting. That adds a totally new dimension in the aerodynamic analysis in this process. And similarly, we are having different kinds of challenges in the other physical domains, which are themselves also quite challenging to tackle. And besides all these complex phenomena, we are also having this interaction between these physics. That way we have a complex multi-physics problem. Again, that would be rather challenging. Now, besides this multi-physics effect, we also have this issue of time scale disparity. What we mean by this is that for the three physical behavior, or the three physical disciplines that we are talking about, they have very different characteristic times. And if you do numerical simulation, then you probably will know that if we do the simulation in the unsteady sense, then we need to determine the time step size depending on the characteristic time. So for the fluid, our time step size needs to be like 1 millisecond. However, for the thermal case, we actually only need to do the simulation at a time step size of 1 second. However, for the hypersonic vehicle, we need to consider the entire flight mission, which might last for an hour or half an hour, which would correspond to like 1,000 seconds. So this means that we need to resolve the fluids at a scale of 1 millisecond, and we need to do that for 1,000 seconds. And this is really poses some intractable computational cost. And then here are some just background on what people are trying to do. People might just use low fidelity models to do this long-term simulation, but this can lead to very wrong results, as was shown in some of the work 3 years ago. Or we can do some very transient analysis, but we can never bring this up to a level of flight region. So here comes, if we really want to do this brutal force simulation using high fidelity models over a very long time, then we'll have this challenge that we would need 1 million steps to resolve the time domain. But for each time step, since we have a very complex fluid problem, it will take many long time for each step. This will add up to weeks or months to do the simulation. So this is a basic challenge in the aerothermal elastic simulation, analysis, and design for hypersonic structures. So the natural thought would be we can somehow just to accelerate the aerothermal elastic simulation. So that way we can perform the analysis faster, and that way we can probably, hopefully, design the hypersonic structure in a tractable computational cost. So just now we identified that there are just two components that's contributing to the computational cost. One is that we have too many time steps. The other is that we have too much computational cost for one step. And people have been tackling these two sides separately. One is to use a more efficient time step coupling schemes to reduce the number of time steps. The other is to use some machine learning techniques to accelerate the computational cost for each step. So I'm not going to talk details about the left part, which is this is more on the numerical computation side. I'm happy to talk if you are an aeroelastician or people who work on FSI after the seminar. And we'll be mainly focusing on the right part, on how we accelerate the computational cost of the fluid solver such that we can perform the simulation in a realistic time. And here by acceleration, we mean accelerating from seconds or minutes down to milliseconds, like maybe 50 or 10 milliseconds. And then over the tackling of this problem, I have developed this hybrid framework. But actually, I think now it should be called hybrid X for extended, because over my doctoral study, I developed the models, as you can see in the white words, and now that I'm in Penn State, I'm developing more modules for this framework. So it's gradually getting more and more extended. And here I need to acknowledge my collaborators like Dr. Singla from my department, where we focus on the lower right part on the thermoelasticity modeling with reduced order modeling. And Dr. Yang, maybe he's not here, when we focus on the large eddy simulation to enhance the fidelity of the problem. Also, Dr. Hanquist, who again, we try to incorporate more complex fluid physics. I will be talking one part of work with Dr. Hanquist in the second part of my talk. But today we'll be focusing on this lower left corner on the reduced order models for the aerothermal loads in hypersonic vehicle. And then my work in machine learning is more of driven by the needs in the different engineering analysis like problems. And for the first part of my work, this is done about 2 years ago, when we need to design the scaled test models for aeroelastic structures, such that we can test it in the wind tunnel. And in this process, I developed some special or some general techniques that can extrapolate a interpolative model. And what do I mean by that? We'll see that in a minute. Okay. So first of all, let me explain what do I mean by scaled models. So if we think about the subsonic case, where we look at a commercial jet, and then we want to test its aerodynamic properties, then we probably want to put it in a wind tunnel. We scale it down and let the wind blow in the wind tunnel, and then we'll get the lift and the moment coefficients that can be converted to the full-scale model. And this can be done relatively easily because we know the scaling laws, namely the necessary similarity parameters to match. So this can be done really easily. However, for hypersonic vehicle, if we really want to do the test, then we need to simultaneously consider the fluid, the thermal, and the structural response, which are actually, in some sense, impossible. There are some work that's done like over 60 years ago, where people have been doing, tried to do the scaling, and it was done for like a very low speed, like a 3.3, a Mach of 3. And that appears to be possible for the aerothermal elastic scaling. But if we want to look at more modern hypersonic vehicles that flies much faster, then it turns out analytically that's not impossible. That's not possible. So that means if we want to test a hypersonic vehicle, then we really need to build such a hypersonic vehicle and fly it in the atmosphere. And this is really, really risky and very costly. And it also takes a really long time. And actually, this is one reason why we are still not seeing real hypersonic vehicles flying in the atmosphere. So here is more like an attempt to say that we actually can scale down the vehicle so that we can test it in the wind tunnel and get reasonable results that can be scaled back to the prototype. This way, we can save the cost and reduce the risk for the hypersonic vehicle development. Yeah, here are some a little more details on why we cannot do the scaling law for aerothermal elasticity. But I guess I'll skip this part. These are just some maths that here showing you that we have some similarity parameters that conflicts each other that will give us different flight conditions for different kind of similarity that we are interested in. To mitigate this conflict in the similarity parameters, we developed this two-pronged approach for for the scaling. Namely, we want to design. We pose the scaling as a design problem. That the idea is to design the structure such that it has a similar response when it is compared to the prototype structure. And if we are able to obtain the two models that behaves in a similar manner, then we can consider that we found this scale model. And this comparison is done in the computational sense. Then there's only one issue that's left. Here we are talking about design. Then we would need to try a lot of different configurations for the scale model. But to do that, we will need to do a lot of computational simulations, which, as we discussed just now, that is really intractable. So we really need to accelerate the simulation to enable this kind of design approach. And this is where the machine learning kicks in. So I'll start with a conventional approach where how we accelerate our aerothermodynamic fluids. So first of all, for our coupled physics, we are more interested, we are more of treating the aerodynamic solver as a black box. we put in the deformation and the temperature from the structure, and then the CFD solver will do some work and then return the pressure and the heat flux. And in this process, we can just replace the black box with a certain reduced order model or a surrogate model, depending on what's your definition of a reduced order model. And then how we construct this reduced order model, then it's straightforward. We produce the input, which are the surface deformation and the temperature. And then going through this black box, we'll get the pressure and the heat flux. Now, what's in this black box? It's just an interpolation between some pre-computed CFD sample solutions. These solutions are generated for different combinations of deformation and the temperature. So that if we want a new deformation and the temperature, then we can put it into this interpolation model, and then we'll get the new pressure and the heat flux for these new structural state. But then there is an issue. For this process, we need to do a lot of pre-computation, and this has to be done for a fixed configuration. This is really inappropriate for design because when we do the design, our geometry of the structure will for sure be changing. And it is really impossible to generate a new ROM for every new geometry that we want to consider. And if we do that, we will need to do a lot of computations for each of these combinations. And this is intractable. So what we have done for this part is then we introduced extrapolation technique based on a mixed fidelity formulation, where we start with our reference reduced order model that's generated for a certain geometry that we are interested in. Now, suppose we want to get the ROM for a new state that might be having a different geometry. We introduce a way to correct it. And this correction factor is approximated using a low fidelity model that can be computed analytically in a very efficient manner. And actually, this approach is very generalizable to many other different engineering problems, as long as we have a low and high fidelity model that we can mix. And here is a quick overview of how this methodology would work. Here in the middle, it's our the error in the reference ROM, which is really low. As you can see, everything is below 5% for the prediction. And then as we change the Mach number and change the altitude, or even change the geometrical scale of the configuration, we are able to keep the error within a reasonable threshold, like roughly 10%, which are sufficient for the design of scaled structures for hypersonic vehicles. So here I skipped quite a bit on how we actually do the design optimization, which is based on Bayesian optimization. And here we'll just jump to this example, where here we look at a nominal hypersonic vehicle, and then we are supposing that we want to scale a certain structure on the surface. And to be more specific, we took a composite skin panel where we have the honeycomb core in the middle, which is for the thermal insulation. And then we wanted to design a scaled model, actually with a uniform material, such that we want to have the panel behaving similarly to the actual skin panel. So we want to minimize the errors in the temperature and the deflection of the two models. So here's the configuration that we are looking at, well, the computational domain. And then we have these different design parameters and also the constraints that we want to have for the to match the similarity. And here are some the wind tunnel that we assume that we are looking at. It's the one hypersonic test facility. And then here are just two cases. One with an extended set of parameters that we can play with. So yeah, so here I'll just show you how the design works or the effect of the work. So in the first case, we are designing with a smaller set of design variables. And unfortunately, we cannot really match the aerothermoelastic responses. Here the dashed line is a scaled model, and the blue line is a prototype. As you can see, in both cases, the error is super large. We can never consider this to be a properly scaled model for wind tunnel testing. And then we can, after we consider a different case, where we expand our design parameter space, then actually something amazing happens. We are able to correct the scaled model response such that it is almost similar to the to the prototype response. And that way we can claim that we actually enabled the aerothermoelastic scaling that was not possible before. And this concludes the first part of my of the work that I want to present here. Now it comes to the second part. So one issue in this first part was that we were more or less considering very simple air model, the gas models for hypersonics. But in reality, we'll get a very severe issue with what we call the high temperature effects in the gas, and this might have a very significant impact on the aerothermoelastic response. And this comes to our second technique that we have to develop over this process, which we introduce a multi-fidelity surrogate for the aerothermal modeling. So we come back to this figure again, and just as a reminder, in the first part, we are mainly looking at this lower portion for the external skins. And in this part, we'll be more thinking about things like the nose tip or the inlet ducts, which is operating at much higher temperature. And at this temperature, we'll be having something crazy. And here's an example. This is a comparison between the computational results and the experimental results on a certain hypersonic test configuration. And we only need to focus on the red curve and the blue curve, where the red curve is a simpler aerodynamic model that doesn't consider the high temperature effects. And as you can see, it cannot predict all these flow separations and the peaks in the surface heat flux. And we have to use a non-equilibrium model that captures all these heat flux. And then we can do the hypersonic structure with confidence. And actually, it's really important to have the correct heat flux prediction when we do the hypersonic structure. And this third figure is from one of our prior studies. It is saying that when we look at, if we use a low fidelity model, the conclusion would be, well, we can just be getting away using a very simple gas model. It will give us a conservative prediction of when the panel fails. However, if we incorporate a little bit more higher fidelity result, then this trend is actually reversed. If you design with a low fidelity model, you'll get a under conservative design, and it's really dangerous if we really have that for the hypersonic structure. So then, but then here comes to an issue. If we really want to incorporate the high temperature effects in the aerothermal elastic design, then we really need a aerothermal model, the fluid model, that accounts for the high temperature effects. But then it comes to an issue where if we just follow what we had in the first part, doing the just the regular Gaussian process regression, we will need maybe 1,000 solutions from things like runs, especially runs with high temperature effects. And unfortunately, if we really want 1,000 solutions of this kind of solution, it might take a month or a year. This is an unfortunate thing. When I collaborated with Dr. Kyle from Arizona, to our disappointment, that if we really want to follow this conventional approach, then we'll never finish our research work. So then we come to the other approach where we say, okay, what if we do this? We start with some very low fidelity models. It could be invasive analytical models, or maybe runs with regular gas models, which are easy to compute, but with lower fidelity. And we just generate maybe 1,000 of it. And then we just generate much fewer, maybe 10 or 20 high fidelity solutions. We use these to correct what we have for the low fidelity model. So to do that, we need to do something what we call the multi-fidelity Gaussian process regression. And the end result is still the same. We'll get a aerothermal surrogate that has high fidelity and still efficient to compute. And by efficient, here we mean that one solution is done in like 50 milliseconds, while if we want to do runs with high fidelity or high temperature effects, it might take maybe 2 days, and sometimes it doesn't converge. So here I'll show an example on the power of this multi-fidelity surrogate, where we look at the aerothermal loads on this flat panel. The gray region can be deforming, and the deformation is according to this sinusoidal response, where A1 and A2 are in this parameter space. And then for the low fidelity data, we consider all these blue dots, and we use these blue dots for the training. And in the meanwhile, we also put in the high fidelity data, also on the same spots of these dots and crosses. But the difference is that we only use the red crosses for the training, and all the rest of the 90 blue dots will be for our testing. So we are only using 10 high fidelity samples to try to get the prediction of a high fidelity solver. And here's the result. Actually, for all those 90 test cases, they are all under 5%, which is really accurate. And here we can look at two special cases. First, let's look at the blue one. that is our best sample. The low fidelity sample, which is a dash dotted line, it is apparently far off from our high fidelity prediction in the solid line. And here you cannot see the blue dashed line representing the surrogate prediction because it's so accurate that it overlaps with this solid line. And the worst case is the blue case, where again, with the surrogate, we are able to correct the low fidelity model to the high fidelity model. And here is just one more example. I'll skip this for the sake of time. But here, actually, you'll see this figure in the in the CAV website, where I modified this a little bit to show how multi-fidelity surrogate works. But essentially, when we do the low fidelity model, we'll get some the right trend, but some very wrong prediction at some regions. And using the multi-fidelity surrogate, we are able to predict something that's almost identical to what we have for the high fidelity solution. And again, this prediction is done in milliseconds as compared to maybe minutes or hours. So then coming to the our origin point where that causes us to develop this model is a high temperature case, where we consider a double cone configuration. And here is a computational result. As you can see that there are so many complex flow features. We have the interaction between the shocks, and we have flow separation, and so on. Really difficult to predict. And again, we consider the configuration with a panel, and we set up the things similar to what we have before, where the blue dots are our low fidelity data. And for the high fidelity data, we look at the red crosses. However, as I mentioned, the high fidelity data are really costly to generate. So we actually only had 11 samples in total. Well, actually, in our ongoing work, we are generating more, but that's another story. And we are having the two crosses at which we check our predictive capabilities. And here I'm giving a feeling of what would happen if we have the surface deformation from the structure, where we can see some spots where we are having really strong, this is actually a shock necking, where we have almost a normal shock forming on the surface of the structure that can cause a very strong heating on the surface, and that can be catastrophic. And similarly, we have a separation in front of the panel. And here are our predictions. For the dashed dotted lines, they are still our low fidelity prediction. They are actually totally off. And our surrogate is able to correct that wrong trend and capture the main peaks in the heat flux prediction. But we have to admit there are still some issues with prediction, where we have some spurious peaks in the heat flux and pressure. But again, this can be improved by adding a little more, just a little more high fidelity samples. And here comes to our case of the aerothermoelastic analysis. On the left, it just shows our deformation of the structure. And then we also get the average wall temperature for the structure, where the analysis shows if we don't care about the wall temperature distribution, then it appears that we get the panel will fail at about 278 milliseconds, which reaches its surface temperature. By the way, so here we are looking at the experimental configuration. So it's really unreasonable to have such a short time frame to have the panel failed. But the methodology can be applied to more practical considerations. Yeah, but if we look at the water temperature in detail, then it's something really dangerous happens. That we are having a very non-uniform water temperature distribution. As a result, as early as 141 millisecond, we are already reaching the surface temperature, and the panel might fail about 50% earlier than what we predicted. And this highlights how important it is to capture the high temperature effects in the aerothermal elastic design in hypersonic structure. And again, these conclusions are enabled by the application of machine learning in the acceleration of the fluid analysis. Now, finally, it comes to our last part, where over the course of the first two parts, I have been always thinking, we really need some real efficient tools to design the hypersonic structure that might have different arbitrary shapes or very complex structures. And here I'll show you what it means by real structures. Here is one configuration from a hypersonic vehicle where we have all these stringers attached to the plate. And as you might can imagine, as the panel heats up, we'll get very wavy structures where the stringer part will deform less and the panel part will just bulge up. So the deformation shape will be really complex. And here is another scenario where people try to do some surface morphing to control the flow separation in hypersonic flow. And in the end, the designed structure shapes like this, which is again much more complex than what has been considered in the surrogate modeling processes. So just to summarize, we are having highly nonlinear deformation and water temperature distributions, and we might be having very strange configurations or shapes of the panel. But for the methods so far, for the machine learning part, we can only consider like a very simple sinusoidal deformation and a fixed shape of the structure, which is really impractical when we want to design something more realistic. So how do we tackle this issue? And it turns out it's possible that we can just use or recycle a very old analytical model called the turbulence viscous inviscid interaction. This is probably some textbook model that would appear in hypersonic aerothermodynamics. And the idea is very simple. We assume that the main stream flow is inviscid, as we would expect from the Reynolds analysis. And then once we have the pressure on the boundary layer as well as the skin panel, then we should be able to predict the growth of the boundary layer. And then from the boundary layer, we should be able to predict the pressure on the pressure and the heat flux on a deformed structure, like on any deformed structure. So that is really good. However, to get some equation like this simple, apparently many physics are missing. For example, the high temperature effects that we were just talking about just now. So it is necessary to somehow augment this simple analytical model such that it can predict the quantities necessary to design hypersonic structure at an accuracy that is close to CFD solution. So here comes to our very new approach fidelity enhancement through a data-driven approach, where so although forgive me for there so many symbols here, but let's just focus on the colored ones, where H is something like a shape factor for the boundary layer. It may not be that accurate, so we try to incorporate a correction factor. Similarly, the skin friction, there might be some inaccuracies, so we get a little bit more corrections here and there. And with these new functions, which is still unknown, we are able to augment our system into a new system of equations with unknown functions. And then we can do an optimization problem such that we find the optimal function forms for these corrections, such that our low fidelity model can predict as well as the computational, high fidelity computational or experimental data. And this way, we are able to capture all the missing physics in the original model. So here is the detailed flow structure, which might be intimidating, but we can go through it step by step. By the way, Steve, how are we doing on time?
Yeah, you 1 o'clock, so we're gonna start losing people.
Okay, yeah. I'll try to cover this in maybe hopefully 5 minutes. Yeah, so we'll start with run solutions, and then the run solution of a deformed structure, and then we have the deformation, and this is the solution that we want to match from the low fidelity TBI model. And then we just want to do this DIE constraint optimization such that we can find the proper correction terms for the cases that we have for the samples. We consider just a few samples here and there that have different amplitudes, the different shapes, a different inflow Mach number. And these are quite sparse, especially when you compare to the earlier cases where we happen to have 100 or 1,000 samples. And then we just do a optimization that minimizes the difference between the runs result and our simplified model result by tuning the beta here. And this is what we get. We have the deformation on the lower left, and then we have the beta, the correction factors that's optimized from the optimization. And then in the lower figure, it shows how the effect of the correction from the TBI model, which is really inaccurate from the black line, and it is corrected into the red line, where it almost matches with the black line. And this achieves what we want. So now once we have these, then we collect these data. These are our training data, where we hope to, we collect these so that we have the TBI solutions as the input and the correction factors as output. So that way we can, once we have such a model, then we can transfer it to the prediction on new configurations without knowing the high fidelity solution. So here comes to the machine learning part, but it's just very simple. We here for enhanced interpretation of the uncertainty, we used the Gaussian process regression, and then the fit looks really great. And then with the Gaussian process regression, we can plug that into our TBI model as the augmented correction factor. So here are some examples. First, we look at a training well, actually, I'll skip this case. Let's directly look at a test case where this training sample is not doesn't appear in our training parameter training samples. And then here are our capability of the GPR-based corrections to enhance the prediction from the blue low-fidelity result to the black high-fidelity result. And further, we can do one more thing, even more crazy, that we can just predict the solution at a very new deformation that doesn't exist in the training data set. And this can never be done by the conventional surrogate. And actually, we can do that. Although there are still some little bit issue at the peak here, but it's apparent that we can correct the blue low fidelity curves to the black low fidelity curves. And also, just want to mention that the generation of the solving of the augmented model, it still takes only like 90 milliseconds when compared to the real high fidelity solution that can take hours to days and so on. So this model, although it's still ongoing, under development, we had only presented a paper in this past SciTech conference. I think it's really promising for the design of hypersonic structures. Yeah, so for the highlights, for the interest of time, I'll skip these and want to mention a few other works that I'm not only doing hypersonics, I'm just organizing my work in a kind of a story. So that's why I have been talking about all hypersonics. I have been also doing something else, like collaborating with Dr. Singala on some kind of system identification work. And surprisingly, my model can be directly applied to some problems in rotorcraft noise, where I work with Dr. Breitner, and we have a recent paper going to be published. And then also I'm looking into something more fancier that we try to use the graph or explore the graph neural networks to capture the dynamics that's on a graph. And this is really useful, or could be really useful, for vortex dynamics and power grids and structural health monitoring when we have a sensor network and things like this. And finally, I'm done. Sorry, I think I'm 6 minutes over, and that's all. Thank you.
All right, thanks, Danny.
Yeah.
If anybody has any questions, please go ahead and ask them. We'll just stay on until all the questions are asked. You can either chat them or use your mics. I guess while folks are thinking, as Danny, the one question that kept occurring to me is, how do you strategize choosing your training points? Right? They were kind of scattered all over the place. I don't know if it was just random or whether there was some real logic behind maybe picking the conditions that you thought would be the most important or most critical.
Yeah, actually, yeah, that's a very good question. Let me maybe go back to, yeah, I'll go back to that slide. So there are so the most can you see that plot there? Yeah, okay. So the most straightforward way is apparently doing a random sampling, but that will cause a lot of unintended sparseness or clutter in the parameter space. So the conventional way is what we do, like the Latin hypercube sampling that spreads the points over a parameter space without using too many points. And here I'm using a slightly different approach that is called a low density sequence. So basically here is a Sobol sequence. It's just a more efficient way to generate these samples. And then furthermore, we can do the sampling more adaptively, especially for the GPRs, because for unsampled location, it can predict the once the model is trained, it can predict the uncertainty in the prediction. And if the uncertainty is too high, and then we can go back to the sample generation stage, add more samples there, and then we go back to train improved model, and then we can iterate until the problem converges. Does that answer your question?
Yeah, great, thanks.
Yeah, okay.
Hi. Hello.
Hello.
Hi. I have another question. So when you are, so you said you're formulating reduced order model from the data, right?
Mm-hmm.
So you said you use POD on the data. Can you hear me properly?
Yeah. I can hear you. Yeah, right. So about POD.
Yes. My question is, how do you decide your dimension of the reduced order model? Like which dimension to choose?
Okay.
When you're
Yeah.
simulating?
Yeah. The question is, when I do POD, how do I choose the model to the number to truncate? Right.
Yeah.
So yeah, that's for sure. You know, the process where we end up with a singular value decomposition, where we have the singular value, and then we can truncate with maybe a 99.9% of energy, which would mean like a 0.1% reconstruction error in the for the POD part. And here I need to differentiate that here I'm slightly mixing the reduced order model with the narrow sense of the reduced order model. I mean, by narrow sense, I mean the reduced order model for dynamical systems, where we need to consider the dynamics in the problem.
Yeah.
But here I'm only using POD for a dimension reduction, because in my fluid problem, it is almost quasi-steady. And we consider the unsteady effects by putting in an analytical term, because the time scale is really short, and it doesn't matter when it compares to the structural response.
I see. Okay. Okay. Makes sense. Thank you.
Yeah.
Hey, Danny, really nice talk. A question like, you are using the low fidelity and high fidelity simulation to construct your GPR model. The GPR model, it's basically a kind of interpolation between the data points. So how do you make sure that your GPR model is not confident about your low fidelity simulations, because they actually have some errors? And in reality, we don't know those low fidelity model errors.
Wait, so you mean, so can you elaborate more on like the model doesn't know the low fidelity model error?
Because you don't want your GPR model to exactly interpolate the low fidelity data points.
Oh yeah, that's right, yeah.
Okay, so that means you need to provide it some information about that, how much confident you are about the low fidelity simulation.
Oh, okay, I see. Well, yeah, so let's see, can you see this slide? I hide this slide. Yeah, but so this requires us to dig a little deeper into the formulation. So in this multi-fidelity part, we have the low fidelity model that as you said, even if we train using this low fidelity sample, it will be very erroneous. And then that's why we incorporate a correction. This, I think, is the term that's what you are getting at. This accounts for the model error in the low fidelity model. And then furthermore, this delta is also a Gaussian process. So this will, when the delta is being trained, it accounts for the existing uncertainty in the low fidelity model. So and then furthermore, sometimes the error can be a distribution over the parameter space. That's why we also include a correction factor, or what we call a scaling factor here, to further enhance the correction for the model error in the low fidelity model.
So the scaling factor is kind of your tuning parameter, which you are trying to get a good, or is the GPR automatically giving you the scaling factor?
Yeah, so during the training, there's actually a Bayesian approach to, I'm sure you know how this the main function is trained, right?
Mhm.
Yeah, so this rho x, it's essentially via some Bayesian like techniques, it will behave the same as the main function. So that way we can have a very rigorous statistical estimate for this correct scaling factor.
Okay. No, thank you. And we can chat offline also.
Yeah, right. We can go to more details.
All right, any other questions? All right, great. Well, that was a very broad talk and a lot of cool stuff in there, just beyond AI and machine learning, but certainly a big part of it. So we're looking forward to hearing back from some of you guys on signing up and getting this group going. So thanks very much, Dan Yang, and for everybody for attending.
Okay. Yeah, thank you for having the talk here. Yeah, and okay.